Okay, welcome to our first unit on rotational motion. We're going to start off with angular motion, the kinematics of angular motion. Now, this is an interesting topic, and unit in general, because usually the perception is that this unit has some concepts that are very hard because they seem very unfamiliar. However, the unit itself serves as a really good review of many of the mechanics topics that we talked about. Essentially, what we're going to be doing in this unit is looking again at things like kinematics, force, energy, and momentum, but from a slightly different perspective. Instead of looking at what we might call linear or rectilinear motion, if we want to be really technical, we're going to be looking at angular motion. So, linear or rectilinear motion, I think, is the proper term. In that type of motion, we are investigating objects as they as they translate, as they move from point to point along some straight or curved line. So the object moves along a straight or curved line. That's what we're really studying. In angular motion, we're not studying objects as they necessarily move from point to point. We're studying the way in which an object or system turns about an axis. Now, this could mean that the object is moving from point to point, but we're more concerned not with the physical distance in meters that it turns, but instead with the angle through which it moves. If we were to measure an angle from, like, let's say where it starts, a line connecting the center of rotation to where the object starts, to a line connecting the center of rotation to where the object ends up. So the object turns or rotates about an axis. Now you might say, wait a sec, we did circular motion. That's all about objects rotating about an axis. That's true, but we were still concerned with the physical distances moved in the linear speeds. We're now going to be looking at the angular speeds, kind of translating that into, okay, what angle per second did it go through? So in linear motion, as I kind of alluded to just a minute ago, we measure distance in meters, typically, in the metric system. In angular motion, we measure angles of rotation. And we measure those sometimes in degrees, but more typically in this unit, we're going to measure in radians, so take an underline there, okay? We're going to be much more concerned with radians. And the second I said that, I know a lot of you got a little jumpy, so we're going to do a quick refresher on what a radian is. First thing I'm going to do is draw a circle. That's a pretty good looking circle, if I do say so myself. And on the circle, a lot of times you'll see that the radius is marked off like this. The definition of a radian is really simple, okay? But it's one of those things where it takes a couple tries to really have that definition sink in for you. A radian means that you take the radius of the circle, and then what you do is pretend that you could pick this radius up, like you could pick this little section up. You lay it along the circumference. So imagine that was a little piece of string, and I could take that little string up and kind of order it so that it lays right about there. Okay, it would lay about this distance right here. Okay, this would also be a distance of r. Now, what the ancient Greeks are famous for is they determined that there was a relationship between the size of the circumference and the size of the radius. They figured this out, and they were like, wait a sec, there's something going on here. They realized that for any circle, it takes 2 times pi radians of length r to complete the circumference. And this is where our term of pi comes from. I think what actually happened with pi is they were first looking at, and I don't know if this is actually true, perhaps they were first looking at a half circle and they found out that, hey, it takes a little bit over 3 radians or 3, if we took 3 radii and put them around the circumference, it takes a little bit more than 3, and it always takes that number. So maybe let's call that number something. Let's call it pi, and then they realize that for a full circle, that just means that it takes 2 pi radians. And again, pi is about 3.14, so 2 pi is about 6.28, and it's an unending decimal, but we don't have to worry about that really. So writing this in equation form, we get that a full circle is equal to 2 pi radians. And if you want to convert that to degrees, we know that that's approximately 300, or that is exactly, I don't know why I said approximately, 360 degrees. And if we're ever given an angle that's in radians, we want to convert to degrees or degrees to radians, vice versa, to convert between the two measures, we simply practice some unit conversion. So you use unit conversion, and the factor, depending on which way you want to switch, 180 degrees divided by pi radians. By the way, the abbreviation for radian is rad, or pi rad over 180 degrees. Okay, so that's all a radian is. I remember from math class, the first time I learned about radians, I was like, I have no idea what this is. It's not a very hard concept. It's a very simple concept, okay? It takes 2 pi radians to complete a circle. A radian just means, it's essentially just take the radius, lay it around the surface. If you want how big a radian is in degrees, it's a little bit over 57 degrees, I believe. Here, let's do this a little more accurate. 180 divided by pi, 57.29. Okay, it's a little bit over 57 degrees. That's what a radian is. Now, what I really want to talk about is the relationship between linear and angular variables. We already have this equation that we just kind of wrote, or actually we haven't written it down yet, but we do have this equation that says the circumference of a circle is equal to 2 pi times the radius, 2 pi r. What is the circumference? The circumference is just the distance around the outside of the circle in meters. It's the perimeter of the circle, essentially. So this is a distance in meters. R is just the radius of the circle. And that leads me to radius, not radians. That leads me to wonder, what does that 2 pi represent? Does it have a meaning? Well, think about a full circle. A circumference means you go all the way around the circle, and we said that in one full circle, the angle you turn about in radians is 2 pi. So it seems like this 2 pi is the angle in radians through which you move while going once around a circle. That's interesting. Does this still hold for similar relationships? Think about if we had a half circle. I'm going to use the variable h to represent the length of half a circle, like this. Okay? What do you think that would be? Well, a half circle is half of a full circle, obviously. So if we just to get from c to h, if we divide this by 2, we get the half circle length, which means we would also have to divide this side by 2, which means we have this. The half circle length would be pi times r, where a half circle length is again a distance in meters, and r is again a radius. Well, wait a sec. Okay, what's the pi mean this time? Well, if it's 2 pi radians in a full circle, wouldn't there just be pi radians in a half circle? And that's the number I have right here. This is again the angle in radians. Matter of fact, this also works if I choose to study a quarter circle length. Q, the distance in meters for a quarter circle. And by the way, remember that 2 pi radians means 360 degrees. Pi radians would be 180 degrees, half a circle. A quarter circle length would be 90 degrees. And you guys might remember from math class, either geometry or trig, that 90 degrees is the same as pi over 2 radians. Since a quarter circle is half of a half circle, if I divide both sides by 2, again, I end up with the following. Q, the distance in meters for a quarter circle, equals pi over 2 times r. This is again the radius. Pi over 2 is the angle encompassed within a quarter circle in radians. So the fact that this seems to work for all these different lengths of a circle hints at a more general equation. The equation is actually something that you have seen before. The equation seems to be that if you take, for for a circle or an object rotating about some fixed point, if you were to take a linear distance and then that is equal to the radius of the circle that you're studying multiplied by the angle rotated through. Now, before I was doing angle times radius, but obviously there's the property in math which says it doesn't matter the order in which you multiply things, so that doesn't really matter. The linear distance, we have given it the symbol s. The radius, that's r. And the angle rotated through, if we're talking about radians, we use theta. So this equation that we have just kind of teased out, this general equation, is actually something that you learned back, I believe, in geometry class. S equals r theta. It's the relationship between the length along the perimeter of a circle, and it says that the length along the perimeter of a circle for some angle that is inscribed in the circle, an angle inscribed with the central vertex being the center of the circle, is equal to that angle multiplied by the radius. If you multiply those two things, the angle in radians multiplied by the radius, if you multiply those two things together, you get the linear distance that angle kind of contains along the perimeter of the circle. And so this is an interesting equation because it allows us to go back and forth between a linear distance and a measurement of an angle. Okay? And that is central to our discussion of angular motion and kinematics. That's kind of how we translate from one thing to the next. So I think I'm going to stop the video there, and we will continue in the next video with talking about angular speed, angular acceleration, and we'll look at and we'll keep going from there.